What is the largest galaxy in the universe? For a long time, the record has been held by IC1101, a supergiant elliptical galaxy thought to be around 2 to 4 million light-years in diameter. It's hard to comprehend just how large that is, but in recent days there has been talk of a new, even larger galaxy, which has caught the attention of several media outlets and science news channels. They all seem to suggest that we have a new king of the cosmos, named Alcyoneus, which is said to boast a diameter of more than 15 million light-years, easily enough to shatter the previous record. But is that what's really being proposed in the original paper detailing the discovery? Not exactly, because Alcyoneus is a radio galaxy, and while it is the largest object of its kind discovered to date, radio galaxies are measured differently to their conventional counterparts. So what is a radio galaxy, and why do they seem to be so much larger than anything else on our established list of known galaxies? Furthermore, why isn't the universe home to more multi-million light-year diameter galaxies? And if Alcyoneus is not the largest galaxy, then how big actually is it? Galaxies are the vast homes of most of the stuff in the universe. Massive, rotating colonies of stars, gas, and dark matter, separated by incomprehensibly vast spaces in between. We are part of a galaxy known as the Milky Way, one of trillions that are thought to reside within our observable universe. They range in sizes and morphologies, from nebulous smears of a matter of light years to vast, complex colonies spanning hundreds of thousands of light years, and pretty much every size in between. However, defining the full extent of a galaxy's size is a tricky affair, because many of them don't have clear boundaries where they start or end. Beyond their core visible components, large galaxies often have even larger extragalactic features. Starry streams, extended disks, gaseous halos, and vast swathes of ejected material. All part of the galaxy's structure, but often not substantial enough to be considered in estimates of its diameter. And so, in this sense, a galaxy can be thought of like a city of stars, rather than a solitary structure. We can place arbitrary boundaries around where we think that city starts and ends, usually based on its stellar density and luminosity. But there will always be houses and roads, or stars in this case, beyond where we draw our border. And so, astronomers tend to class the end of a galaxy as the place where the stellar density drops to 1 star per 100 square light years. But even defining where that is isn't always straightforward, including when it comes to our champion galaxy. As mentioned at the start, the long-term record holder for the largest galaxy is IC1101, a supergiant elliptical galaxy at the heart of the Abell 2029 cluster. It was once believed to be more than 6 million light-years in diameter, more than twice the distance between us and our nearest spiral galaxy neighbour, Andromeda. Imagine double that entire expanse and more, permeated by a dense colony of more than 100 trillion ancient stars. However, this 6 million light-year estimate has been dialed down somewhat in recent years, reason being because the primary stellar diameter of the galaxy is thought to be smaller than the full radiating area. Around half of the galaxy's stars and luminous output can be found within a concentrated region near the centre, around 400,000 light-years across. The remaining length of the galaxy owes to a much larger, but considerably dimmer and more diffuse halo, which gives the galaxy its multi-million light-year extensions. But even with the more pessimistic estimates, it still tops our unofficial list for the largest known galaxy, and its diameter is the record to beat. But then, there's that recent discovery we alluded to at the start, Alcyoneus, which is claimed by some to be more than 16 million light-years in diameter, equivalent to more than 150 Milky Way diameters. So it would seem we have a new champion easily, right? Well, most likely not, unfortunately. Alcyoneus is a radio galaxy. It's still the largest radio galaxy, but these radio signatures are not classified or measured in the same manner as normal galaxies. When probing the depths of the universe, the majority of galaxies that we can detect do not reveal themselves to us in the optical wavelengths. We can't see them, but we can listen for them. Galaxies produce many types of electromagnetic radiation, and while visible light suffers greatly from the effects of extinction as it travels through intergalactic gas, radio waves are able to pass through these mediums relatively unfazed. This, coupled with our excellent capacity to conduct radio astronomy, means it will come as no surprise that most of the distant extragalactic objects that we have discovered have shown up in radio surveys. Quasars were first detected via their radio emissions. Before that, they went unnoticed as they were indistinguishable from the Milky Way's stars. And like a quasar, a radio galaxy is thought to be the product of the galaxy's energetic core, also known as its active galactic nucleus. We know that at the centre of most galaxies there lies a spinning supermassive black hole surrounded by gas, and when this gas feels the immense tidal gravitational forces exerted by the black hole, all manner of extreme natural phenomena can occur. A quasar occurs when the friction produced around the black hole releases blinding amounts of light. But a radio galaxy occurs when particles from those surroundings become funneled onto one of the black hole's polar axes by strong magnetic fields. Any matter that reaches one of these poles is blasted out into space with so much energy that the particles within accelerate to near light speed velocities, carried away by twin relativistic jets. As gas caught up in these jets grows hotter, its charged electrons become unbound, igniting the matter into a plasma state. The streams of plasma, filled with free-roaming charged particles, are expelled from the galaxy's core at relativistic velocities for thousands of light-years, slowing down eventually, but continuing to carry far beyond the bounds of the host galaxy into intergalactic space. The moving charged particles generate magnetic fields, which curve the paths of other charged particles and accelerate them. This process releases synchrotron radiation, which is visible in a broad range of wavelengths. And it is for this reason that we can detect radio galaxies. The synchrotron radiation is detectable in optical wavelengths, ultraviolet, and even X-ray, but they also glow in the radio wavelengths, allowing us to detect and map thousands from both Earth-based and space-based telescopes. As the supermassive black hole's jets continue to erupt, they supplement these streams with more plasma, increasing the internal pressure and causing them to spread out. And so often accompanying jets do we see larger plumes or even lobes of dispersed plasma. These lobes constitute some of the largest extragalactic features we know of, glowing with synchrotron radiation. The full structure, consisting of the galactic nucleus, the twin jets, the accompanying lobes, and any other radiative features, are what defines the length of a radio galaxy when we detect one from Earth. The broad smoothness of these ejections implies that they are created by synchrotron radiation, and the presence of synchrotron radiation in turn implies the existence of ionized plasma, free-roaming electrons, and magnetic fields within the material. This is not an uncommon or unexpected process for a galaxy either. The Milky Way has its own pair of radio-loud magnetized outflows, albeit not as substantial, generated by its supermassive black hole. We can also see one such jet playing out in real time by turning our attention to Messier 87. In summary, we're pretty confident on our understanding of how a radio galaxy is created. What we don't know, however, is the overall effect on the intergalactic medium these ejections have. We don't know what happens within the vast quantities of plasma once they have been cast into the void. But if they ultimately lay the foundations for new star formation so far away from the host galaxy, then it adds the most extreme of extensions to consider when trying to determine the galaxy's size. We're also limited in how we can study radio galaxies. We struggle to work out their age and how far along they are in their emissions life cycle. We can only infer the minimum amount of energy a radio galaxy would require, and we don't know what affects one's radio power. We're not sure what factors, other than time of course, determine whether jets become elongated plumes or wider, more dispersed lobes. And most of all, we're not sure what the underlying mechanism driving giant radio galaxies is. Giant radio galaxies are the largest objects of single galactic origin in the universe. They have jets and lobes extending hundreds of times beyond the bounds of their host, creating radio-loud structures on megaparsec scales, not simply explainable by the age of the emissions. There's not an agreed threshold for what makes a giant radio galaxy, but the boundary is often taken to be between 0.7 megaparsecs and 1 megaparsec, so that's between 2.2 million and 3.2 million light-years. If there is a natural process driving these emissions to such mind-blowing scales, then we've yet to understand it. But studying giant radio galaxies to identify physical and environmental commonalities represents our only way of learning more. We've identified more than 1,000 of these giant radio galaxies in recent years, most in the Northern Hemisphere. All 1,000 of them have lengths at least the distance between us and Andromeda, and more than 100 of them exceed even the most generous estimates for IC 1101 at 6 million light-years. But the 10 largest sit above or around the 10 million light-year mark. But remember that this is the estimated length of the galaxy's radio emissions, and so that does not often mean that the host galaxy sitting underneath is that large. Of course, we can consider radio emissions to be an extension of a galaxy worth measuring, but it would be like including the smoke rising from a chimney when trying to measure the height of a house. In any case, however, the newly discovered giant radio galaxy, Alcyoneus, is still a record-breaking object. It is the largest of all giant radio galaxies, identified by a team of researchers headed by Martin Uy. It was found in a self-described stroke of luck by the team, as its faint, remote emissions are easily missed when surveying the full extent of the radio sky. But it was nonetheless uncovered by the team during a reprocessing of the second data release of the LOFAR 2-meter sky survey. The Low Frequency Array is a pan-European network of radio telescopes surveying the sky as one, with more than 20,000 ears at 52 sites across the continent. Its broad range of wavelength coverage makes it an excellent tool for spotting radio features indicative of underlying galaxies. The radio signal in question is dubbed J14200545, while its host galaxy is designated SDSS Data Release 12 J081421.68 plus 522410.0. But of course, both of those designations are terrible, and so they gave it a more fitting name from Greek mythology. Alcyoneus is named after one of the giants who went to war with the gods and battled the hero Hercules, so a fairly appropriate name for a giant radio galaxy. Although interestingly, it seems that wasn't the preferred choice of the authors of the paper. The original publication contains a footnote which appears to suggest that they wanted to name this radio galaxy Pallas, another figure in Greek mythology. But this name proved to be too common among asteroid designations, and so Alcyoneus it remains. Located in the constellation of Lynx, this radio galaxy constitutes an enormous three-part structure of a pair of twin jets and two vastly extended radio lobes. The full extension measures a whopping 5 megaparsecs in length, equivalent to some 16.3 million light years. That's not just larger than the distance between us and Andromeda, but larger than the entire expanse of our local galactic group. But when mapped onto the sky, it becomes small enough to be missed, due to its vast intergalactic distance of 3 billion light years. Consequentially, these emissions have taken billions of years to reach us, and probably look very different as they are today. But as we see them, they are the largest emission of radio ejecta by a galaxy ever detected, its great plasma arms reaching out into the darkness of intergalactic space. However, beyond this record-breaking radio ejection size, Alcyoneus has no other oddities worth mentioning. It appears to be a completely normal radio galaxy. Therefore, if there is an intrinsic or environmental characteristic which enables the formation of very large radio galaxies, Alcyoneus most likely possesses it. In pursuit of identifying this key characteristic, Ui's team attempted to reverse engineer the properties of Alcyoneus's underlying host galaxy and its surroundings. We know that the host is most likely a giant elliptical galaxy. The invariable majority of radio galaxies are. With this in mind, the team derived estimates for the mass of Alcyoneus's stars based on the galaxy's luminosity. Rather unexpectedly, they found the host galaxy to be slightly less luminous than they were expecting, based on observations of other giant radio galaxies. After probing the galaxy's luminosity, they were able to estimate its stellar mass, that is, solely the mass of its stars, thought to be around 240 billion times the mass of the Sun, around 5 times the stellar mass of the Milky Way. Similarly, the galaxy's central supermassive black hole was estimated to be around 400 million solar masses, 100 times heavier than the Milky Way's central black hole, and 4 times heavier than the black hole lying at the heart of the Andromeda Galaxy. So we're dealing with a pretty large and pretty massive elliptical galaxy, but probably not a record-breaking one. And certainly not one that appears to come close to rivaling IC 1101's black hole, thought to be 100 times more massive than Alcyoneus's, at 40 billion solar masses. In fact, both the luminous output of the galaxy and its correlating mass estimates were found to be less than what was predicted given the properties of similar giant radio galaxies. This implies that Alcyoneus may have formed in a less dense region of space, and not, say, at the heart of a crowded galaxy cluster like IC 1101. As such, it doesn't seem like there is a strong relationship between a galaxy's size and mass and the size of its resulting radio galaxy emissions. Instead, scientists now think that the key to radio galaxy growth may lie in the environment in which they emerge. We know that Alcyoneus lies somewhere within a galaxy filament, an inconceivably huge wall of weakly interacting galaxies propagating across billions of light years. These filaments link up to form the long branches of the cosmic web, the invisible universal network of dark matter which acted as the skeleton of the early universe. If Alcyoneus, the largest of all radio galaxies, lies in a less populated region of this cosmic network, then perhaps giant radio galaxy growth actually favours lower density environments. This led the authors of the original paper to suggest that radio galaxy emissions may be enhanced by thermodynamic interactions with the cosmic web itself. But there is a significant amount of observational work required before we are able to follow up on such a wild hypothesis. However, the bottom line is that, as a non-radio galaxy, Alcyoneus is, unfortunately, nowhere near our list of contenders for the largest galaxy. It is by far the largest radio galaxy, but if we subtract its sparse, low-pressure radio structure, the actual galaxy underneath probably sits somewhere in the 200,000 to 300,000 light-year range. Still impressively large as galaxies go, but just not record-breaking. How large can galaxies really get? And why does IC 1101 appear to be such an unmatched exception? We know that galaxies grow via mergers, the process of attracting one another, colliding, and coalescing each galaxy's constituent stars and gas. These collisions produce enormous asymmetric gravitational reverberations which fling stars and matter outwards, enlarging and elongating the resulting structure. And so, assuming an indefinite number of collisions, there shouldn't be a hard limit on how big galaxies can become. And yet, the vast majority of large galaxies that we see, their visible components at least, rarely seem to exceed the 300,000 to 400,000 light-year range. There are a handful of exceptions, including those others within our unofficial largest galaxy list, but these dimensions often consider the extended extragalactic features beyond the main body of the galaxies themselves. Broadly speaking, galaxies of IC 1101's size seem to be a real rarity in space. It appears as if there is some sort of limiting factor, or perhaps a number of them, which constrain a galaxy's potential for growth. IC 1101 probably owes its abnormal size to its crowded galactic neighbourhood. This implies that it was once an even more populous area in the early universe, filled with dozens of smaller gaseous galaxies, which came together to form great golden titans. Every time the budding IC 1101 absorbed a smaller galaxy, tidal forces would have invigorated its star-forming gases, leading to rapid, persistent, and productive star formation, equivalent to thousands of new suns a year for billions of years. This stubbornly high star formation rate, coupled with its selection of devoured galaxies, left the giant bustling with an enormous colony of more than 100 trillion stars, scattered and flattened into a disk shape of record-breaking size which faces us directly. This could be a consideration for when trying to find large galaxies. IC 1101 happens to be visible from Earth at its largest extension, but other elongated galaxies of similar sizes may lie at orientations which hide their largest extensions. Not to mention the existence of even larger galactic disks and halos which are often rendered invisible by their enormous distances. Another consideration is that, while IC 1101 is a star-bursting galaxy, this relentless rate of star formation by which it grew so large came at a price. The galaxy is now dying, having exhausted its gas reserves. This monster galaxy maximised its star-forming potential earlier than it might have if it were smaller. And with no new game-changing galaxy mergers on the cards in its future, it will only be able to recede as its stars begin to fade. All galaxies will eventually meet this fate, especially with the accelerating expansion of the universe. As galaxies are pushed apart, they will fall out of reach of potential collision partners, and the availability of the gas they are left with will decline thereafter. Perhaps the vast majority of large galaxies in the universe proceed to elliptical or lenticular morphology via collisions, and manage to reach scales of a few 100,000 light-years, but become unable to grow any larger once they've cleared out their surroundings. Perhaps the collision process is capable of giving rise to galaxies with multi-million light-year diameters, but it is simply not that robust. Perhaps the areas of space best suited to the runaway accretion of crowded galaxies evident in IC 1101 are rare, and there may only be a handful of such environments in the observable universe. Perhaps there are factors which work against the process, contributing to the deceleration of structure formation. It has been suggested that radio galaxy ejecta in intergalactic space may produce a feedback mechanism which slows the formation of the largest galaxies, preventing IC 1101 analogues from forming in all but the most chance of circumstances. Or perhaps it is just a matter of perspective. After all, there is always a significant light delay when looking at other galaxies. We can only ever see space in the past. Perhaps if we saw the universe in its true current form, we would see galaxies comparable to IC 1101 more frequently. And likewise, perhaps if we existed later in the universe's life, even larger galaxies would have time to form. There's a lot of ifs, buts, and I've lost track of the amount of times I've said the word perhaps in this video. However, if nothing else, IC 1101 does show us that galaxies of multi-million light-year diameters can form through the collision process, however rare they may be. And given our inability to see and measure the majority of galaxies, it's likely that there do indeed exist others of record-breaking sizes which we just haven't found yet. If IC 1101 is not unique in its size, then there will almost certainly be a larger galaxy out there somewhere, formed in an even more idealistic environment. And who knows how large that could be. But sadly, Alcyoneus is just not that guy, and IC 1101 remains the king of the cosmos. But for how long is the question? These record holders are almost always temporary. And with next generation telescopes like James Webb finally searching the skies, it's hard to imagine how we won't find something even larger in years to come.